everybody. I'm Andy Buffler. I'm the head of physics at UCT. Welcome to this somewhat strange presentation. I mean, the first time I've had a UCT Open Day in a form such as this, and I suppose it's a little bit strange for you as well. But what I'll do is I'll talk for about 10 minutes, and I'm sure many of you have a whole lot of questions that you may want to ask. I've done this presentation for a number of years, so hopefully I anticipate quite a few of your questions. Presumably all of you are somewhat interested in physics, and so we're going to sort of talk about a little bit about what physics we do at UCT in terms of our research. But of course, physics is all about understanding nature better. Model building. So if you're excited about technology and good at solving problems and things like that, I guess that you may well be interested in physics, and hopefully we'll see you in our class for first years next year, which is here's a recent photograph of our class for physics majors from 1 or 2 years ago. So hopefully you see yourself there next year. And of course, we deal with all sorts of classical and modern physics. For example, some of you may have heard of Maxwell's equations, which describe the nature of light, quantum mechanics and special relativity, the two bastions of modern physics that come about over the last century only, that underpins just about all of modern technology. We wouldn't be having this conversation with each other if it wasn't for quantum mechanics driving the mechanisms inside the devices that you're using to watch and listen to me, for example. So if any of this is exciting for you, then maybe we'll see you next year, and hopefully we do. We live in a real world, and physics allows us to build models of the real world that we see around us, and this can be a straightforward and sometimes a very complicated process. And in fact, at UCT, two of the main areas of physics research have to do with looking back in time as far as we can possibly look, and also recreating the conditions of the early universe. And I'll talk to that a little bit just for a few minutes. So we can look back in time by looking out into the universe, and of course, the further we look out, and the further we can reach with our technologies in terms of observing, the further back in time we go. And so certainly nowadays we are edging towards observing objects at the very edge of our universe, and that's very exciting. Another way to look back in time is to accelerate particles to great speeds and smash them together. And the more energy you put into those collisions, the further back in time you go, because you're approaching conditions of the early universe. And I'm sure many of you know, but you might be interested and excited to know that colleagues of mine within the departments are involved in two of the very big experiments at the Large Hadron Collider at CERN. We have colleagues who were involved in the Higgs discovery, for example, and continue to be on the ATLAS experiment, which deals with more aspects of particle physics, looking for strange new particles that can only be observed within conditions that are within like the early universe. And the ALICE experiment, or ALICE experiment, smashes charged particles together and recreates conditions of the early universe, which is sometimes known as the quark-gluon plasma, which is the soup of energetic particles, which allows us to understand how matter came about in the early times of the universe. So if you come to my departments next year, you'll meet colleagues who spend time at CERN, and certainly all the postgraduates who are involved in these experiments will go to Geneva at some point. And even during this COVID time, some of my colleagues will have been traveling to CERN to be involved in this work. There's a bit of a shutdown at the moment at the accelerator, but they plan to start up again next year with the next series of runs. Another part of our research within the department has to do with applied physics and metrology, which is the science of measurements. And in our building, if you visited us for real for this open day, but you didn't, it's crazy. But if you did, you would stand in the foyer of our physics building, and beneath the foyer, one level down, is the coldest place in Africa. It's a 6 millikelvin refrigerator dilution refrigerator, which allows us to slow atoms down, slow electrons down, so we can literally pick them up one by one and move them around and manipulate them in different ways. And so that's certainly a leading facility in Africa and the Southern Hemisphere. We also have a small accelerator in the building that we use, that we produce neutrons for various applications. We have a number of PET scanners that we pull apart and reconfigure for tracking the movements of particles within fluids that are in different industrial systems, such as flotation cells and tumbling mills and so on, and a whole number of other things. And that's within a research center that I lead within the department. Some of you know that, of course, nearby there's Itembe Labs. It's a national facility where there's a number of accelerators that I and other colleagues use for nuclear physics research in different ways. And what I'm showing here is one of the cyclotrons, the big cyclotron at Itembe Labs, and we have a strong collaboration, a strong connection with Itembe. All right, so in a nutshell, that's what we do in physics. So we have a part of our research fabric that is about high energy physics, exploring the very nature of the early part of the universe, so we can understand the building blocks of matter better. And that's a number of big international projects. In fact, the Atlas collaboration is one of the largest, if not the largest, science collaboration on the planet. And that's very exciting. So if you come and join us, you will be part of one of the largest, if not the largest, scientific collaboration on the planet. And I'll talk about astronomy now in a sec. And then on the other hand, we have very, very exciting laboratory facilities that allow us to explore different parts of matter by either freezing it to very cold or smashing it together with our accelerators. And the important point to remember is all this experimental physics is related to the ideas of physics, which are encapsulated within theoretical models, and this critical interplay between physics theory and physics experiment and observation is what makes physics physics. And in some ways makes it more challenging for students, because not only do you need to have a good handle on the mathematical aspects of models, you also need to deal with experimental aspects. So there's this constant interplay between experiment and theory that is unique to physical sciences and physics in particular. And of course, astronomy is basically also physics. It's quite an interesting situation at UCT where we have a separate department of astronomy. It's very rare internationally. Normally there's a department of physics and astronomy in contexts such as ours, but for various reasons we have a separate department. They're in the same building, and we are very close, very friendly, and share many students between us. Of course, astronomy has a very high profile of research in South Africa. You've all heard of the SKA and Meerkat and things like that, and SALT, the big telescope, and it's all about having different instrumentations to measure electromagnetic radiation in different parts of the spectrum from the universe. And modern astronomy has instruments that allows us to measure across the entire electromagnetic spectrum, all the way from energetic gamma rays. For example, the Hess telescope in Namibia is a good example of that, all the way through ultraviolet to obviously optical, and then down to the low energy, which is the radio part of the spectrum. And that's where South Africa has a leading role to play, because SKA is a square kilometer array, and the precursor Meerkat is looking in the radio part of the electromagnetic spectrum. So I've got two very exciting pictures to show you. And you've seen this in some form before, that of course you can look back in time by smashing particles together at CERN, or by looking further and further into the universe. And it's all about looking at the early parts of the universe and understanding the evolution of the universe and the nature of matter and its interactions. So there's a picture, again, you would have seen something like that. Of course, there's at the top, we've got some of the Meerkat telescopes, and then on the left is this big SALT telescope at Sutherland's, and then a new instrument that's been put onto SALT recently, and at the bottom, the sort of general landscape of the Sutherland's observatory. And these are the two pictures that I was keen to show you. These haven't been published yet, I got them from my friend who's head of astronomy just the other day. And in the top right-hand corner is a picture from Meerkat, one of the better, most innovative pictures from Meerkat, showing a radio picture of radio part of the spectrum of the center of our galaxy, the Milky Way, and that is being now observed with detail that has never been observed before, and very exciting. And here is another two photographs on the left and the right, again looking at the regions near the center of our galaxy with the so-called Meerlicht telescope, which is a very, very high resolution CCD camera. And if you look at those photographs, you need to sort of peer in and look very carefully. There are hundreds of thousands of millions of stars and galaxies in those frames. It is a resolution of the night sky that is unprecedented for land-based observatory. And the exciting part to realize here is the Meerlicht, which is looking optical, is now for the first time tied to parts of Meerkat, which look in the radio part, and they both look at the same parts of the sky. So again, this is a leading aspect of astronomy in South Africa, that we can look in multiple parts of the electromagnetic spectrum at the same object in the sky at the same time. So that's very exciting. All right, so again, come to UCT and you can be part of that. Right, so let's do some of the more mundane parts. I'll spend a very, very few minutes. And if you want to post stuff in the Q&A, questions in the Q&A, please do that. So if you do a physics degree, you basically need math. You need a lot of maths. So typically you would do maths, physics, and applied maths in your first year. And then you do one more course in your first year, such as astronomy or statistics or computer science or chemistry, and you can be free to do that. Some students like taking non-science subjects like English or philosophy, and that you can do that as well. But really, you really need physics, maths, and applied maths in first year for physics and astrophysics. In fact, you don't even need astronomy 1 because you can pick that up later. And then, as you've heard probably previously now, you've got 3 subjects in your second year typically, and 2 subjects in your third year. So it's 4 + 3 + 2 is a 9-course degree over 3 years. Popular majors with physics, of course, astrophysics is a popular major. Actually, physics and applied maths is more popular in many ways. And then, of course, maths and computer science kind of fit in within the cluster, but we get some other stuff as well, like physics and philosophy and class. Okay, will be quite popular. But really, for physics, it's not a straightforward degree in its difficulty. So really, you need to do a lot of maths and just dealing with what careers. If you've got to really ask what careers, you probably shouldn't be doing physics, because I just say on the side that we've been quite for many reasons. I think we understand physics is actually growing at UCT. So the last 5 or 6 years, we used to get produce about 25 majors in third year physics, and we're up in the upper 30s nowadays, and that's a very unusual growth for physics and astronomy in terms of international trends. So solving problems, working with numbers. Nowadays you need to learn how to program. We use Python quite a lot, so learn Python if you want to. In the meanwhile, jobs in academia and industry, of course, are important. But our graduates go into business, into education, into data science is a big theme at the moment, and so on. So again, a question that pops up: what should you be doing as a high school student at the moment? And I would say just work on your math. Really, physical science is important, but you'll do that anyway. But don't skimp on your maths. The more math you can do, the better. All right. Don't cut corners. Don't say, "Oh, I'll understand this later," or "I didn't get geometry," or "I didn't really understand series." Understand it all. The better you are at math, the better you'll do it. You'll do it physics. Okay. And so just I'm finished with my slides. So I've got some questions popping up. So I encourage you to type questions into the Q&A. I won't publish them. I'll just answer them verbally as we go along. So will classes be online next year? I really hope not. I mean, we were hoping classes were not online going to be online this year, and for obvious reasons, we had to go online for classes. But having said that, we're running as many labs and tutorials on campus for physics as we possibly can for our courses. So we've had a really busy time. Obviously with COVID, we need to thin out the classes a little bit in terms of labs. But we're really trying to get as many students on campus even now at this time to run labs, especially at the senior years. What subjects are included in physical science? I'm not sure what you mean there. But that would be at school would be physics and chemistry, but of course they're both helpful. When you earned your degree, do you recommend working at NASA? Absolutely. I've got two students working at NASA at the moment. One's doing a PhD at Pasadena, and he's building a radiation detector that goes at the tip of a drill that's going to go on a mission to land on an asteroid and drill into the asteroid and do really interesting things by doing some analysis of the material inside the asteroid by using some radiation to activate the atoms, and then the radiation detector is going to measure the gamma ray signals from that activation. So that's one of my postgraduates working there at the moment. But of course NASA, they're going to have to you have to be really good to work in NASA, of course. Can I transfer from engineering to astrophysics? It's not that straightforward because you've got to do a bit of science courses, but engineers, the astrophysicists are really keen on engineers because you can see how much engineering goes into SK and all that. And so knowing a little bit of astrophysics and going to engineering would be really useful. How many first-year students get accepted to the program average every year? I don't know the answer to that. You must ask the science talk about that. But we have about 4,000 applications for science. For 500 places. That's kind of how it goes. It is competitive. Do well at your maths, and you got a good presentation. Thanks for that. How many students accept for first year? About 500 in science. How many students? Yep, fine. How many first year students you take in 2021? Is there a limit? There's a limit. And in science, there has to be a limit because it's a really world-class degree at UCT. Really a world-class degree. Remember, our students who come out with a physics major and then go to honors and then master's PhD, they're all over the world. All right, if you get a science degree from UCT, I'm talking about physics and astrophysics, you are literally a commodity of the world. We've got it's a very difficult aspect of our lives at UCT. I've been at UCT for 30 years. That we produce these outstanding students, and of course we want to keep the postgrad students in our department to do outstanding work, but of course the opportunities for our students to go to Geneva, to all over Europe, all over the United States. We've got students in Switzerland, Germany at the moment, United States, Sweden. I mean, it is something that is a bittersweet thing for us to produce outstanding students and then allow them to go and study overseas. But that's obviously it's good. Hopefully they come back. But the takeaway message is UCT Physics and Astronomy is a strong research department. All right, we are involved in many of the leading physics and astronomy projects in the world. We have a reputation for being very useful in our niche areas, and so if you're joining a department that is vibrant in the research space, but we also have a outstanding undergrad teaching program. It's a challenging teaching program. Many of our students find it very challenging, but we are producing more physics graduates over the years than we have ever done. So it's certainly something that is achievable, and when you pop out the other side, you're going to be part of a physics community that is global, but also part of a physics community that's doing research that is not just internationally relevant, but has impact locally in South Africa as well through things like the SKA and the applied physics research that we do that is very locally applicable. If you need more, if you need further questions, you may email me. So here's a website for physics and astronomy. So if you have a physics question, go to our website, find my email, and please pop me a question, and I'm sure I can manage to ask you. What we've got here are some of our students from the last few years. This fellow on the rotating stool is one of the school outreach program we run every year. So there's some, we get the schools in. We couldn't do it over COVID, so you probably all missed out. And we run very innovative whiteboard tutorials as well in labs. So Garth, I'm on 20 minutes, and I would like to say thanks to everybody who joins. I hope you enjoyed the talk. I'm sorry about the format. It's what we're living with, and I hope to see all of you at UCT next year. Great, thanks Garth. Thanks everybody for joining.